This lecture is going to relate Newton's law of universal gravitation to circular motion, which we learned earlier in the year. The quote we have says, "Aim for the moon. If you miss, you may hit a star." That's especially important in this unit. It is somewhat difficult mathematically, but you have to aim for as high as you can and hope for the best. So the goals are: the students should understand that gravity acts as a centripetal force. So in other words, it takes planets and stars and makes them move in circular motion. And that you just should understand the role that gravity has on escape velocity. In other words, how fast an object has to be moving to escape Earth's gravity, and how fast an object has to be moving to be placed in orbit. So here you see that because we have a centripetal force that's directed toward the center, and now we know that's the gravitational force, we can say that that gravity is the cause of this particular centripetal force for an object moving around the Earth or the Sun or something along those lines. So if you take a look at this, we have the centripetal force formula and we have the gravitational force formula, and what we can do is we can set them equal to each other because the centripetal force is the gravitational force and vice versa. So because of that, you can see that one of the mass terms is going to cancel out. And what mass term that is it's actually the mass of the orbiting object. The mass of what is causing the gravitational force is still very, very important. You also see that one of the r terms cancels out. And so what you end up with is this term right here, which more often is simplified as Vt squared or just Vt. And then you would take the square root if you exemplify it that way. But Vt squared equals gm1 over r. Alright, this example says, why is mass irrelevant in where you place a satellite in orbit? So it doesn't matter if it's a big communication satellite, a very, very small satellite, something you're launching in. Mass actually has nothing to do with any of those, and let's explain why. So we said that when you have an object that moves in circular motion, it has to have a centripetal force. Now, the centripetal force that is provided to a satellite is the gravitational force that exists between the satellite and the Earth. So, because of that, we know we have a centripetal force. Well, the formula that we learned for centripetal force is mvt squared over r. Okay? With this mass being the orbiting mass, or let's say the satellite. We also have the gravitational force formula. We know that the gravitational force is what actually supplies the centripetal force. We know that the gravitational force can be calculated using Newton's law of universal gravitation, which basically says you have a universal gravitational constant, you have mass 1, which is the mass of the Earth, you have mass 2, which represents the satellite, and you have r, which is once again the distance between them. Since the centripetal force is the gravitational force, you can say Fc equals Fg, or if we were going to plug in our things, you have mvt squared over r equals m1 m2 over r squared. Left the g term off. Okay, so now realize that this is the mass of the satellite, and m2 was once again the mass of the satellite. So these two things are actually the same thing. If you have the same variable on both sides of the equations, you can actually eliminate it. You can also eliminate this r term right here because you have an r on the other side. Now, this r term actually cancels out completely, but it actually just gets rid of the square value right there. So what we end up with is Vt squared equals g m1 over r. If you can see, there is no mass of the satellite anywhere in this equation. This question says you have a satellite that orbits 100 kilometers above the surface of the Earth, and it gives you the radius of the Earth as 6,378 kilometers. And it asks how fast it's moving, and it gives you the mass of the Earth. So let's go ahead and draw what we have going on here. You have the Earth, and you have a satellite that is in orbit around the Earth. So I'll say that's my satellite. This right here is the center of the Earth. Now, why is that important? That's important because you have this distance right here as 6,378, and you have this distance right here as being 100. Now, realize that whenever you're doing the gravitational force calculations, the R value that's represented as the distance between the objects does not represent this 100 kilometers, but it's from the center of one object to the center of another. Now, the center of a satellite, the satellite's going to be at most 2 or 3 meters big, so because of that, it's really irrelevant. But this right here, this 6,378, is actually very, very relevant. So the radius for our calculations is actually going to be 6,478 kilometers, which then I can convert to meters as 6478000 meters. So it's really important that we take into account the radius of the Earth when we're looking at this calculation. So it says we want to know how fast the satellite is moving. We know that we were going to have to use our tangential velocity formula relationship, vt squared gm1 over r. Okay, that's the form that we originally had, so we can say, okay, the tangential velocity is going to equal the square root of g. Remember, g is the universal gravitational constant. You can find it on the star formula chart, and it is 6.67 times 10 to the minus 11th. You also have m1 that gives you the mass of the Earth, which it told us was 5.98 times 10 to the 24th. That was in kilograms. So now we can just plug in, we say 6.67 times 10 to the minus 11th times, 5.98 times 10 to the 24th, and all of that is divided by our radius value, which is 6,478,000 meters. Whenever we do this, we realize that the square root, everything is under the square root. So we have to do all of our math first. 6.67 e minus 11 times 5.98 e 24. Hold on, I got in the wrong mode here. 6.67 e minus 11 times 5.98 e 24 divided by 6478000. So that right there gives you a pretty high number. Whenever you look at that number, you should say, well, that's a pretty big number. Do not forget to take the square root. As you'll see a little bit later, this number is actually very, very close to the speed of light, which is not relevant. It's not accurate for a satellite. So you should be able to say, got to take the square root of that, which gives me a more reasonable number of 7,846 meters per second. Now that is still a very high number, but it makes sense. You're launching a satellite on a spacecraft using rockets to place it into orbit. So you're actually moving it very, very, very quickly. Okay, so let's make sure our units match up. So originally we had this G term right here. That G term represents Newton. So the universal gravitational constant is Newton meter squared per kilogram squared. We're going to multiply that by kilograms because that's what our mass was. We're going to divide it by meters. Okay, and what we're going to end up with is a Newton meter per kilogram. And we're going to have to take the square root of that, which we'll do in just a second. But right now it looks like our units aren't going to match because remember, we're trying to get to meters per second. Until you remember the definition of a Newton. Remember, a Newton is a kilogram meter per second squared. So when you take that into account, where you're multiplying by meters and you're dividing by kilograms, which is still there, meters is going to combine to become meters squared. Kilograms is going to cancel out entirely. So now I have meters squared per second squared, of which I need to take the square root. Taking the square root of the top and the bottom gives you meters per second, which is exactly where you want to be. Alright, in this example, he says a geosynchronous satellite is one that completes an orbit every 24 hours at 36,800 kilometers. This is what is the velocity of the satellite, and then it gives you the mass of the Earth. It also gives you the radius of the Earth.
There's actually two different ways to solve this. One of them would be just simply using the tangential velocity calculation that we learned earlier this year, and that's Vt equals 2 pi r over t, because you are given the orbital period of 24 hours. In addition to that, you're given the radius as being 36,800 kilometers. So that would allow you to calculate the velocity that way. Now you can also do it using the gravitational formula that we've talked about. Vt equals the square root of g m over r. Now, if you were to do this calculation, you would get something slightly different in each one, because it turns out that satellites are not in circular orbit. It turns out that they're actually in an elliptical orbit. So you're actually going to get slightly different answers, because this equation right here only works for circles, whereas this one works using gravitation, and it is approximating circular motion, but it's not quite as confined as this. So you get some close answers. Also, this 36,800 represents the total center to orbital distance. So this term is actually irrelevant whenever you're looking at this particular problem.
Now, escape velocity is just a little bit different. It's very similar, but there's an extra factor here, and this is this 2 factor. So what you get is the escape velocity squared is equal to 2gm1 over r. And the reason for the 2 is not quite apparent, but instead of just maintaining the orbit, you're actually trying to break the orbit. And this term actually comes from conservation of energy, which we haven't quite talked about yet, but conservation of energy allows you to determine the escape velocity in order to escape the gravitational field. So it's very important that you be able to distinguish between orbital speed and escape velocity, or orbital velocity and escape velocity, and know whether that 2 is supposed to be here or not.
Okay, in this question it says, sketch the shape of the graph showing the relationship between tangential or escape velocity and mass. And so what we've seen is velocity squared, we're going to call it escape velocity, is equal to 2gm1 over r. Now, if we were looking at the graphical relationship between two variables, we circle those variables. Those are the two variables that we're interested in. So in this case, if we were to look at it, we would say, okay, everything else goes away, and what I'm left with is v squared is equal to m1. We substitute in y squared equals x, which is a somewhat rather difficult graph for us to graph in a graphing calculator. So what we're going to do is we're going to go ahead and take the square root of both sides, and when we do that, we will get y is equal to the square root of x. But here's the key thing. Whenever you take the square root of x, it's actually plus or minus the square root of x. Okay, so what we get is we would get something along the lines of this. Now, the question is this is the graph we would get mathematically, but does it make sense to include the whole graph in terms of physical principles? And the question is can I have a positive mass that would give me some sort of negative velocity? And the answer is, of course I could. I could get a negative velocity value. That just means that the direction is different. This direction as opposed to this direction. Now, because it's actually ends up being a squared value, later on, this will actually go away because we're going to have a squared velocity value. But for now, actually, both values will work. All right, and this question asks us, what is the escape velocity of Earth? And it gives you the mass of Earth, and it gives you the radius of Earth in terms of to the surface of Earth. So how fast does an object at the surface of Earth have to be moving in order to escape Earth's gravitational pull? So what we want to do is we want to use our gravitational formula. So we have the surface of Earth. We want to know how fast something has to be moving right here in order to escape the gravitational pull of the Earth. So we should know that that's going to be pretty fast. We're looking for the escape velocity. So how fast does a rocket have to go to, say, go to the moon? And the formula that we've learned is the square root of 2gm1 over r. Well, we have the g value, that's our universal gravitational constant. We also have our mass value, and we have our radius value, which is converted to meters as that. So this is a pretty simple calculation. We just plug our numbers in and we say, okay, the escape velocity is equal to the square root of 2 times 6.67 times 10 to the minus 11th times 5.98 times 10 to the 24th, and then all of that divided by 6378000. So when you plug this in, you get 2, let's get the right function here, 2 times 6.67 e minus 11 times 5.98 e 24 divided by 6378000. And we want to do is we want to take the square root of that value. And when we do that, we get a very large value, something like 11183.7 meters per second, which is very, very fast. Now, one of the questions that I usually get at this point is this how fast the space shuttle has to be going to leave Earth's atmosphere? And it turns out it doesn't have to be moving quite this fast. And so the reason why is we calculated how fast an object has to be moving at the surface to escape Earth's gravitational pull. What happens is the space shuttle actually accelerates this whole time, and it doesn't reach its final velocity till it's somewhere right here. When it reaches that final velocity, this distance term is actually increased quite a bit. It may have gone from 6,378,000 to maybe 6,478,000, but that has a significant impact and reduces the overall velocity that's necessary. However, if you have an object that you launch, like say from a catapult system or something along those lines, it has to be moving this fast at the surface of the Earth to escape Earth's gravitational pull.
So you should understand that gravity acts as a centripetal force whenever we're talking about planets or satellites or something that's orbiting another object. And you should also understand that gravity has a very important role in determining how fast you have to be going to escape that planet and how much fuel a rocket would need as a result, or how fast an object has to be moving to actually establish an orbit around Earth, like a satellite that's used for, TV and things like that.